think technology is moving rapidly and continues to move rapidly. I think what students will learn is that learning doesn't stop when you graduate from college. In fact, it's a lifelong process, and what you want to do is have the right associations and collaboration within your company or outside resources like the Blended Learning Program from IEEE to continue your education and continue to learn about advances in design and verification. It's getting complex these days, in fact, to the point where we have more verification engineers than designers on a project, just amplifying the impact that getting the design done right and verified is important, and taking more talent, more people, and you have a great opportunity in the years ahead. But I leave you this, that this is just the beginning. Your learning is going to be forever. You know, I think when you leave the university, you know how to design. You've perhaps learned the VHDL or Verilog languages. These IEEE standards offer a solid base from which to do design, but there's more to doing design, and you'll learn that when you get out of college. As design sizes increase and as things become bigger and smaller geometry factor into this, we find that the problems that exist in a design are hard to find, hard to isolate, and hard to fix. And there's new technologies that are coming, new standards that support these technologies, and these are things that you probably won't learn in class because you're just trying to master the fundamentals of getting design done. You start with simple things first and build up. Once you begin to design on smaller nanometer semiconductor technologies, what you're pressed with is the need to be able to debug those designs that are extremely challenging, extremely complex, and just the variety of technologies that are applied for verification in this space will go beyond probably what you've been exposed to in your baseline education. So these challenges, by the way, don't just end and aren't static, but will renew themselves every 18 months in pace with Moore's Law. I think the base one is that you're able to actually create perhaps the RTL in VHDL or Verilog, or that you can express a system design in System C. These are all IEEE standards. That's the starting point. But to become an active and productive member of a team, you have to learn more. And in fact, there are a lot more IEEE standards that are important in the development of semiconductor technology as well. Verification technology, you may have learned design work, but you may not be familiar with object-oriented programming. You're going to have to get the skills in that area. If you know how to program in C++ or Java, you have good exposure to object-oriented programming. And in the System Verilog case, we do exploit object-oriented programming there as well. And you should probably learn those type of techniques and technologies. Now beyond that, in large designs, the ability to isolate, correct, and change and detect errors in a design really mean you have to begin to learn more advanced things. We've added assertions in the System Verilog language. Those are extremely powerful so that when you are verifying a design, it not only checks to make sure the design is doing what was intended, but it also flags times and conditions that were not intended, and you can go and correct those. Engineers often don't think about the unintended consequences of how they put blocks together, designs, but with assertions, these things are easily flagged and detected. So again, education to learn more about those type of techniques is important. But as you join design teams, I would immerse yourself in how your design team approaches verification and immerse yourself in learning about those techniques and technologies.